Sorry, I was cut short by a faculty meeting. So we're going to continue where we left off, and this is with the iron spheres. And again, we're knocking these two spheres together. We have one sphere that's covered with aluminum, and the other one that's covered with iron oxide. In this reaction, the aluminum is going to become aluminum oxide. So it's going from a neutral state to a charged state. And since it's a metal, the charge is going to be a positive. So how do I go from a neutral state to a positive state? We're going to be losing electrons. In the total of this reaction, we're losing 6 electrons. What's going to happen is these 6 electrons are then going to combine with the iron oxide. So we're just going to take a look at the iron. And we have the 2 irons, and each of the irons has a 3+ charge in the iron oxide. Again, nothing's happening to the oxygen, so we're not really concerned with that. So we have 2 irons each that are lacking 3 electrons. They're in their ion state. And here come 6 electrons. These 6 electrons are going to be attracted to this. And what it's going to do is it's going to be producing 2 irons that are going to be in the solid state. So in this reaction, we go from aluminum solid to an aluminum ion. And we go from an iron ion to being solid aluminum. So let's go back to this over here. So again, this is the pitcher. This is the oxidation reaction. This is the catcher. This is getting the electrons. This is throwing the baseball. This is catching the baseball. So this is being oxidized. So I'd like you to write being oxidized. And this is something that's going to be seen on the homework assignment. Since this is being oxidized, what it's doing is it's losing the electron, it's throwing the ball. Since it's throwing the ball to the iron, it's enabling the iron to get the electrons. So again, here's the pitcher, here's the catcher. So the pitcher is allowing the catcher to catch the ball. So the ball being thrown again is the electrons. So while the aluminum is being oxidized, it is reducing, it's throwing the ball, it's reducing the iron. It's taking the iron from the charged state and it's making it into the neutral state. So this is called the reducing agent. The reducing agent. And vice versa. Over here, the iron, this is being reduced. The iron is becoming reduced. Being reduced is it's gaining the electrons. It's being reduced. Well, since it's being reduced, what's it getting reduced from? Where is it getting that ball? Where is it getting the electron? It's getting it from the aluminum that's throwing it. So therefore, it's enabling the aluminum to be oxidized. So this is going to be the oxidizing agent. So to recap and to summarize these redox reactions, we have something that's being thrown, which is the electron. If you're throwing it, you're being oxidized. If you're catching it, you're being reduced. Now, not all reactions can be spontaneous, as we had learned previously. And we have to take a look at what's called the activity chart. Okay? For example, these are some of the elements that we've seen today: aluminum, zinc, iron, and copper. And this reactivity chart goes down in this direction, meaning that this is the highest on the activity chart, and this is the lowest on the activity chart. So let's take a look at this one right here with the zinc and with the copper. The zinc and the copper, the zinc is, again, this is what's being oxidized. The zinc is being oxidized, and it's throwing the electron. It is the pitcher. It's throwing it to the copper, who's the catcher. this is being reduced. Now think of this like a hill. At the top of the hill, we have the zinc. And on the bottom of the hill, we have the copper. And this electron is going to naturally go down into this lower state. It's going to go from a region of higher activity to lower activity. If we take a look at this reaction, the zinc, which is in the solid state, okay, we're going to take this up here, plus the copper that's in the charged state will become charged zinc and solid copper. This is the reaction that takes place because the zinc has the ability to be oxidized and to transfer the electrons to the copper. Let's reverse and switch this scenario. Imagine if I had copper, okay, and I combined that with a zinc ion, like zinc sulfate. If I put copper into zinc sulfate, absolutely nothing would happen. That reaction does not occur. Because in order for this reaction to occur, the copper would have to transfer its electrons to the zinc. But copper can't transfer it to the zinc because the zinc is higher on the reactivity chart. It's higher on the hill. It naturally can't go to that higher state. So naturally, this reaction occurs in this direction. It goes down. This is what's being oxidized. This is what's throwing the electron. This is what's receiving the electron. The only way that we can go backwards like this is if we have a rechargeable battery and we actually supply the energy to push it back up the hill again. But that will be coming in a future lecture. Let me go ahead and show you the end result of our sample. And look what's happened to the color of my liquid. It started off as a bright blue, and now it's very, very pale. Again, the blue was the copper, and we had this metal zinc. What's happening is the zinc is transferring all of its electrons to the copper, and the copper, which was dissolved, is now becoming solid zinc. It's taking those electrons, and it is now creating a solid. So there's still a little bit left of that zinc plate. Actually, there's not much left. Oh, there it is. So there's the zinc plate, and there's all the reddish copper that we are creating. Those are redox reactions.